Sorry about the delay. Now, let's see if it says that it can see the license. Okay, so we're sitting over here, but I had a problem that I wanted to do. It was right there. Okay. Okay, so if you saw, was it Friday? If you saw Friday's thing, I was in the middle of working this one, and I sort of dropped out near the end, and I think I left it hanging, so I need to figure out where I am, where I was. Doing accelerations. I got down to this point, because I was doing accelerations about this link AB. So, although the subscripts here get changed, the equation sits right here. This is the acceleration of link AP, which is this one. I started here. So I'm kind of review for a second. So I started AP, which is that link. And he gave me the omega, gave me the alpha. So I came down. I put the omega, the alpha. Here, I'll do it this way. Put the alpha in here because that's what he had. I found the R, which is pretty simple. So I was able to put this matrix into here. Then let's see if I can still do this. Yeah, it's a little slow, but I can take it back out. Then I took the omega, which was given right here, the scalar value, you square it. So this one's a scalar. Then I took the vector, which is the same vector that sits right here, goes right there. I multiplied it, carried it down. I realized that there was going to be only a J component. And I think I did this in octave when I did it. So I end up with the acceleration of A being a component, which is going directly down, and then a component here, which is the centrifugal component. And that goes back towards the center of rotation. In other words, if you look at the thing, this thing is spinning. This is the centrifugal component right here, going this way. This is the tangential component here. And I'm not sure I drew them to scale, but it doesn't really matter. Because one, well, I may have. One is twice as, this one's twice as large as that one. Next thing I did is I started looking at the next link, which is this link A to B, from here to here. Took the picture, copied it. First thing I did is I determined what the vector is that originates from A and is drawn to B. And that was what I had here. That actually came from early in the lecture because I did and used this, took this problem and I did it in an instant center first. So I determined the link from here to here, and then the link from here to here, and that was the 2 cosine 30 and the 2 sine 30 and the 2 cosine 30. So I've got my values here and here. So I kept using that, went back, got to, give me a second, I need to shrink way down, apparently. Didn't come back. Uh-oh. Okay. I don't know what it's doing. Okay, that's right here. So that's where I got these components from. And then I realized it went to the left. The vector goes to the left. And the vector also goes down, so they're both negative. This is 1 from that component back there. So then we realize, okay, so I took this term right here. What I did is I took the alpha out so I could do this inside octave with a number right here. So that's the reason you see a 1 right here. There usually is an alpha there, but that's multiplied times it. So I think we're okay there. Put in my R, because I'm supposed to. Then I took the value of omega AB, which was given, but we found, because usually it's not given. We put it right here. Then we took the R vector, which was this one, and we simply copied it right there, which is what we get right here. Then I have to carry my acceleration to right there. I think that's where I left off. And what I had done here is I had copied that from above so that you could see that the structure for the velocity with the omega ends up being the same structure for the acceleration, but with the alpha. And so this is kind of now in the way. So what I'm going to do my best to get it out of the way and complete the problem. Okay, so I'm getting it out of the way. Now, let's see. Let's go ahead and do this. I'll go ahead and do octave. Sorry. Okay, so there's my octave. So I don't know if I'm going to use it or just do this by hand. So I'll start with this one, and I'll do it this way. Okay, so alpha AB. And I know if I take this one and this one, copy that one down, I'm going to get a number. So what I'm going to do is put this alpha here. And I'll go 0, 1, minus 1, 0, minus J. And now that I've got all this in the way, if I take this and knock it out, take this, knock it out, and take this matrix, copy it down here, I'll get 0, 1, 1.7321, and 0. And if I can do the K, I think I'm going to end up with nothing. So swipe that and that, take that and copy it, take the determinant of that, and minus 1. That's a 0. So I'm not going to get anything out of that. That's going to be 0. And actually, I should put the other stuff. And instead of me rewriting it, I'll do it this way. For the time being, copy, and I'll put it about right there. So I just copied it, pasted it right there. For that matter, I can go ahead and just take that out. If I look at the cross products, I get alpha AB I, and that's going to give me nothing. It's going to be minus a minus, so I'm just going to get a 1. So here, I'll do that. This one comes a minus that one, but it's a minus, and another minus. So it becomes a minus 7321 J, and there isn't a K, minus. Okay, so what I'm going to do is I'm going to subdivide this. I'm going to focus on this one for a second. So I'm going to focus on each one, and I guess what I'm going to do, I'm going to try to use this to calculate it, and that's going to be 1.15 squared first times 1. Well, I'll tell you what I'll do. I'll do that, and then I'll multiply it times 1.7321. So what I get out of here is, okay, a minus gives me a plus. Okay. That'll be 2.2907 I, and that's going to be a plus. Oh, and a minus becomes a plus. Okay. And that's going to be that, oh, yeah, that's going to be 1.3225, and that's a J. And then carry this along for the ride. Okay, so here's the funny thing. If we stare at this, let me move this keyboard tray out of the way. If you stare at this thing, you'll realize that this is the centrifugal and this is the tangential. So what I'm going to do is I'm going to look at this for a second and say to myself, does it make sense, the values I'm getting? So if I copy or just reuse, I'll just reuse this. I'm reusing this sheet. It says for this component, so I'm going to stare at this individually, whatever the vector length in the x, I turn it and make it go in the negative direction, multiply it times 1.73, and that should be the direction of this vector. So what I'm going to do, I'm going to go to, it says go to the right a little bit, and then it says go in the negative direction, almost twice as large, and that should be my component. Now, I'm sort of faking it here, but it should be exactly tangential. Now, the reason I'm doing this is because this, in this particular way, is you got an X, you got a Y. This is a positive omega and a positive alpha. Since I do not know the alpha of this thing, I'm assuming it positive. If I'm assuming it positive, that means it goes this way. That means that this tangent component goes that way. If I had assumed it the other direction, it would have gone exactly the other way. But the key is, it is tangential. If you want to prove that, you can dot this vector with the vector that sits in the bottom of here. And what you find out is the 1 times this plus, that'll become a minus 1.73. And this times that, that'll become a plus 1.73. And you add them together, you get 0. So in fact, it is perpendicular. So what that's showing is, if you look at that lower thing, that's a vector right here. And this vector right here is like this. And if they are perpendicular, then the dot product is 0. And in fact, they are. And this is what I've got drawn there. So everything seems to be okay there. The next thing is this funny thing. Now, what's weird here, if you look at this, it is a constant times this vector. Now, unless I goof up somehow, this vector was defined as the r vector, which is right up here. So by nature, if I drew it, it goes in the plus I and the plus j, but the plus I is the one that's almost twice as large. So here, let's do the j, let's do an approximation of the j. going into plus j, say a distance this far. So then take that value, multiply it times about 1.73, and draw that in the positive direction. Positive direction means positive this way. And it turns out that vector goes right back down. It should go right back up the r. Makes sense because this vector is in fact that, which is a scalar times the vector in the negative direction. So in fact, everything seems to be okay. This one's hung around for the ride. So it's basically the acceleration of the point right there. So hang on. Now I'll run backwards. And I've got one other contention to make. The contention here is that this little thing, or this drawing, it doesn't matter which one I do, there's no way that point B can accelerate this way. It can only go either this way or that way. It's going to either accelerate, decelerate, whatever you want. So you have to choose a direction. I'm going to choose a direction. We choose this one, and I'm going to say that's the acceleration of B. And I'm just going to call it AB times I. And I guess I did that already. So here it is. It can only go that way. So now I come down here, AB, a scalar unknown, AB, I. So now if I look at this, okay, this is where I should stop and look at this for a second. Give me a second. Let me put all the stuff around it. Now I'm going to identify all the ones that have an I component. And then I'll identify all the ones that have a J component. And then what I'll do is I'll do my I equation here, and I'll do my J equation here because they're independent. Okay, so my I equation becomes, let me tilt this thing like that out of the way. So here's my I equation, AB, and now just grab them. Alpha AB, and I take my next blue one, which is 2.2907, and I take my last blue one, which is 8. And then I'll do the J, the green. There's nothing on the left-hand side. There's no I's over here. You get minus 1.7321 alpha AB. My next green is that one. So it's 1.3225. And then my last green one is that one. So it looks pretty, you got two unknowns and two equations. It looks pretty apparent to me that it's possible that I can get my alpha completely out of that one. And the way I do that is just alpha AB. I don't know, I guess I can move it to the far side. And then that makes it 1.3225 times 4 divided by 1.7321, or a negative something or other. Let's see what I get. 1.3225 minus 4. Then I divide that by 1.7321 minus 1.54, 0.54, 58. So now that I got that alpha, I can turn around and stick it right back in here, and I can get the acceleration of B equaling to, and I just put it in there. So I think I'm going to put these first. Well, I'll put the other one first. Minus 1.5458. I copied it right. Plus 2.2907 plus 8. I don't know what that is. but I do have part of it up there, and I can do plus 2.2907, and then plus 8. Okay, okay, 8.74. Right, okay, hang on. 8.7449. And, oh, okay, let me look at the picture. So there's my acceleration of B. Okay, and I was trying to find the units here, where this is meters. Yeah, these are in meters. Okay, so I'm going to throw a monkey wrench in here now. And the monkey wrench is kind of this, and this is part that I shouldn't do, but I'm going to do it anyway. So now you have acceleration of B, 8.74, let's just say it's 7.74 meters per second squared. You got a rod here, and this piston. Now, I'm not supposed to do this yet, but I'm going to go ahead and do it. And this isn't part of this chapter, it's part of the other chapter. So if you break this apart, and you say this is like a 10 kilogram piston, and who cares what this thing is. So this is the rod. I'm splitting them apart. Now the first thing I found out is it's positive, so the acceleration is kind of going to the right. So if this thing's worth 8 kilograms, the next thing you do, sum of the forces in the x equal mass times acceleration in the x. So actually just copy that. Copy that. Let's say there's no, like it's really oily. There's no friction. And so then you just have the force that this rod, you know, I'm just calling it, I don't know what I want to call it. I'm gonna put it in there in this direction. If I do, then it has to go equal and opposite. So this I'll call it Fx. Fx. So just Fx is equal to 10 times 8.74, or 87.4 newtons. And that's the part of chapter 13. I don't remember the chapter number. So all this happens in chapter whatever, the next chapter. But the key is, kinematics is basically finding velocities and acceleration. Kinetics is basically, after you find the acceleration, you just multiply it times m times a, and on the left-hand side, the sum of the forces, you do a little free body diagram. And that's it. So this part is actually harder. It scaled it from 1 to 10. I'd say that's about a 9. This part, scaling to 1 to 10, maybe 2. So, and technically, some people may view that as a 1, and some people may view that as a 10, but I was trying to be conservative. So, I mean, geez, look at that. Here's the part of the problem that deals with the kinetics, and the rest of the whole page deals with the kinematics. So kinematics is, these are tough problems. These are long. They're not really tough in a sense. They're very, very long. So you got to start and you got to work your way through the whole problem. So I think that's what I'm going to do, is do this for like 2 more, maybe even 3 more class periods. Where'd it go? Oh, here we go. Come back. I may do this 3 more class periods where I find 3 or 4 really good problems here that have, I mean, this one's kind of, I don't know, that one, because the problem is the velocity is only going to go this way, it's going that way. This one's good, but the problem is you got a velocity exactly going that way, and you got one going this way. Ooh, oh, see that one. That's, I'll get excited there for a minute, but I'll just go in. This is pretty good. I might pick that one. I'm going to go pick the ones that are in the assignment as well. That one, I like that one. So I tell you what, here, let me just identify a whole pile that I'm going to work. I don't know why I'm erasing these. I like those. We'll definitely do this one. Let's see, did he give it? He gave us the alpha, and he gave us the omega. So we'll do this one. Then we'll go in. I'm going to do this one. I do like that one. I like that one. This one seems hard, but actually it's not, because you got this going this way and this going this way. That tells you that the omega here is equal to 0. That makes it easy, so I think I'll do that one just because of that simplification. This one, let's see. Velocity's going that way. Velocity's going this way. So if you drew an instant center thing, this link appears like it's rotating about that spot. So I like that one. Determine the angular acceleration of, oh, he does, he gives you that. Yeah, let's do that one. We'll do that one. I guess. Oh, that looks funny. Or do we want to do this one? I don't know. Those both are actually very similar. I'll do that one because this one actually has, I think the asterisk means it doesn't have an answer in the back of the book. What is the difference between that and that? Let's see. What is he asking different? Remember that extension? And the acceleration of point C. Where is point? Oh, that there. So he's just asking two questions about the same thing. That's probably enough problems for it. Although that one looks pretty cool. Although I'm not sure. The mechanism produces intermittent motion of link AB. Okay. If the sprocket is turning with the angular velocity, angular acceleration, and the angular velocity of that, the sprocket, which one? I guess that's the sprocket, because those are the numbers. Determine the angular velocity acceleration of link AB, that's that link. At this instant, the sprocket S is mounted on a shaft, is separate from the collinear shaft attached to ABA. So in other words, this is not welded to that. We can move independently. The pin is attached to one of the chain such that it moves vertically downward. So he's basically saying it's moving this way. Okay, that looks challenging enough. We'll do that one. God, that's enough problems right there. But this is the toughest section in the whole course. So I think it's prudent to spend a little bit more time working a whole bunch of problems. Because the rest of the course goes pretty quick and is considerably easier than this. So, I don't know. So does this kind of make sense? I mean, it's kind of weird. This is the hardest part. But, I mean, I would say, okay, chapter 12 was really long and annoying. This one is very hard and tedious, and you work a problem. It'd take you an hour and a half, 2 hours. The next chapter, Sum of the Four Physical Mass Times Acceleration, that is like incredibly easy. Then the energy methods, even easier, and then impact just becomes fine. So I mean, this is the toughest part. And so that's why I spend like an extra couple weeks on this. Just work a bunch of problems, and you know, since I'm recording them, you can go back and look at them. So, sorry for being late. Driving along at the construction thing at a giant hole in the ground, in the middle of the road. I got the feeling that maybe the water main was broke because of the line. And they're just now fixing it. Of course, it's way out in the country, so. Okay, sorry for starting late. I will take, well, now the water will be fixed by Wednesday. They should have the water fixed. I'll take it. All right. I didn't do a word of the day, did I? That's too late. You too.